Hi, I'm Guido Christen, Principal Scientist at Chemical Computing Group. Today I'm going to show you the SiteFinder application in Mo. Probably one of your first tasks in a structure-based project is to identify druggable binding sites. This is a twofold problem consisting of identifying cavities in the 3D structure of your target and scoring their druggability. Most SiteFinder application is a fast geometric tool that is not biased by any training structures and can be run even on large new structures. It will address the identification of pockets and score their druggability in one go. In 2020 there was a Nature paper on identifying challenging binding sites. One of the examples used was an A2A signaling protein. So I'm gonna take that structure for this demo too. It is a GPCR that has a known orthosteric site, but in drug design, modulating its function by targeting an allosteric binding site is at least equally important. So let's try to identify these sites too. The PDB code of this structure is 5G53 and I will download it directly from the RCSB website. When you download structures from the PDB, Mo will offer you the option to build the biomolecule assembly or the crystal neighbors. I will go with just the asymmetric unit. The asymmetric unit contains 2 copies of the structure. To get rid of one of the copies, I will use the sequence editor, which is our central entry point for all our protein-based applications. I will delete chains B and D. And that gives us just the adenosine receptor and the GPCR bound to it in the main window. As we are interested in targeting the GPCR only, we can also remove the adenosine receptor, so I will delete chain C. And now we have just the GPCR left on screen. But before we can start any modeling, we must make sure that the structure in the main window has no issues like missing atoms or missing loops that would lead to problems during minimization, for example. In Mo, you can use QuickPrep to fix all these problems with one click. Actually, 2 clicks. Let me reopen the panel so that we can discuss it while it is running. The panel has 3 sections. The first section deals with structural issues like missing atoms, missing loops, partial charges, setting the optimal protonation state for all residues in the protein, and optimizing the hydrogen bond network. In the section below, I can set tethers to keep the backbone geometry intact and fix atoms that are not involved in ligand binding. And in the last section, I can control the minimization to relax the structure with the current force field. And after the structure has been prepared, I will annotate it for better orientation. Mo comes with several pre-aligned and superposed protein families that we use to identify the different domains and annotate them. As we have a GPCR on screen, I will use GPCR class A. And the annotation process will also create sets for these domains that you can see in the System Manager. The System Manager is our main panel to organize the system and control the rendering. At the bottom of the list, you see that Mo created sets for the transmembrane helices and for the extracellular loops. For designing a drug, we concentrate on these transmembrane region, and I would also like to include helix number 8 as it is an essential structural motif for mechanosensitive GPCRs. And to make it easier to refer to this selection later on, I will create a set and I will call it helices. And now our system is set up and we can start the identification of druggable binding sites with the SiteFinder. The SiteFinder panel also consists of 3 parts. On top we define which atoms should be used as input, and I will use the set we just created. In the middle section the pockets will be listed, and at the bottom you can control the rendering. When I click apply, you will see how fast the algorithm works, as the results show up almost instantaneously. The algorithm is based on alpha spheres. Any 4 atoms on the protein surface define a sphere. If there is no other atom inside the sphere, we call it an alpha sphere. Spheres with very small radii are probably located in tight packed areas and not reachable by any ligand, so we remove them. Spheres with large radii are located on the outside of the protein and can be removed too. The remaining spheres we classify into hydrophilic, if at least one of the defining atoms is hydrophilic, and hydrophobic, if all defining atoms are hydrophobic. You can control these parameters in the settings panel. For hydrophilic spheres, we use a minimum radius of 1.4 angstrom, which corresponds to the size of a water molecule. For hydrophobic spheres, the minimum radius is 1.8 angstrom, which correlates to a methyl group. Finally, we cluster the spheres to remove those which do not add additional informations to the results. Now let's check the results. The first site is the orthosteric binding pocket. For each site detected, Mo will list the size, the PLB score, the number of hydrophobic and side chain contact atoms. The final column lists the contact residues. To identify the orthosteric pocket, the PLB, short for propensity of ligand binding score, is the most important one. It is a knowledge-based score based on amino acid compositions of ligand binding pockets in the PDB. So as we expect, the orthosteric pocket got a high PLB score. As we go down the list, you see that the PLB score drops. But as we are now searching for allosteric pockets, that is expected. The third pocket is in contact with helix 8, and that is the allosteric pocket discussed in the paper I mentioned before. Further down the list, we find a larger site between the dark red helix number 5 and the orange helix number 6. And this pocket is also discussed in literature. Let's go back to the orthosteric site. The default rendering style is alpha centers. If you would like to get a better feeling for the available pocket volume, you can switch to alpha spheres. And this visualization can be used as starting point to develop a pharmacophore query. To define this site as binding pocket for a docking simulation, I can create dummy atoms. This is very handy for apo structures where you have no ligand to define the binding pocket. Especially for large proteins, the view might be cluttered and it is hard to spot the contact residues. To make that easier, you can isolate the backbone. And for sequence-based work, you can have Mo select the context residues in the sequence editor. That comes especially handy if you look at selectivity. Here you can see that the orthosteric site is in contact with 3 of the helices. I hope that what I showed you in the last couple of minutes will help you in the future when you must find druggable binding pockets in a protein target. If you have any questions, please reach out to us at support@chemcomp.com.